Hello and welcome to 36th lecture of video course on tribology. Topic of the present lecture is the friction and lubrication of gears. In previous lecture we started gears, we defined profile of the gears and mentioned there will be some sliding other than at the pitch point, and that sliding causes a friction. In addition, as we use lubricant to reduce the friction, but there will be another disadvantage of that will cause a disadvantage, that will be churning effect. Only one or two gear teeth will be in mesh, remaining gear teeth will be without meshing. So, they start splashing the lubricant and there will be some losses, friction losses, energy losses because of that. So, we are going to discuss this topic in our present lecture. Say that we can start thinking about the bare surfaces without any lubricant. When we were discussing about the friction at the different tribospheres, this was the first word we call the dry friction. And to illustrate it, to demonstrate it, we have shown that these gear pair in a mesh, and we are able to see there is a meshing. At this point there is a meshing. If I zoom it, we are able to see the mesh and we are able to see some sort of elastic deformation on this surface. If surfaces are without any lubricant and they need to rotate, naturally there will be high friction. Coefficient of friction may even reach 0.6, 0.7. If surface finishes are not very good, surfaces are not harder, they deflect easily, then that will not be desirable, because gears are used for the power transmission, not for power losing effect. We want to transmit the power as much as possible. Efficiency should be 100%. Our target will be always efficiency should be 100%. And if we take care properly, we can reach to 99%, 98%. Reaching beyond that will be just impossible unless we change the technology. From mechanical point of view, that will be pretty difficult. Now, this can be demonstrated. Why there is a friction? We are able to see there are some asperities. Whenever there is a mechanical contact under load condition, there is a possibility of deformation of the surface, and because of the asperities, there will be interlocking, and this interlocking may be based on just abrasion or may be based on adhesion of the cold welding. In particularly dry surfaces, cold welding is a predominant phenomenon. Coefficient of friction majorly occurs because of the adhesion, because of the cold weld, other asperity, and we need to reduce as low as possible. That's why so this figure shows this asperity. If we try to penetrate another surface, it will be difficult to remove the pinion over the gear. However, we know very well that in a normal atmospheric condition, there will be always a one contaminated layer on the metallic surfaces. What we are discussing over here, particularly for the metallic surfaces, and mostly gears are manufactured having metal surface, even though we know very well that polymers have started, or the polymers have been used to manufacture gears, but for the low load applications. Even in this case, those cases also there will be friction losses. What we are talking here only for metallic surfaces, and we say the metals, if kept in environment, it will absorb few layers, maybe the angstrom to the nanometer level thick layer, but there will be some kind of the layers on the surface, and that is shown with this white color layer on the surfaces. We are showing that both the surfaces, maybe the pinion surface and gear surface, both will have some sort of contamination layer without any lubricant. We are talking that it is without any lubricant, and these layers are generally having a lesser shear strength That's why the relative sliding will be simpler compared to the parent material, compared to the bare materials, without any contamination layer on that. And this has been studied in our friction module lectures, maybe the third, fourth lecture, which was discussed in detail, that if there is a bare surface and kept in environment, there will be some sort of oxidation, and that oxidation itself will generate low shear strength lubricant layer on the surface, but still this can be treated as dry lubrication. Now, as this is been shown that there is a contamination layer on that, the question comes, can we really go ahead, can we design this lubricant layer our own using some sort of solid lubricant? We have studied solid lubricants. We know about the molybdenum disulfide. We know about the graphite surfaces. Even we know the Teflon coatings. Those are the solid lubricant layers. It can be designed as per the requirement. What we discuss, it is a natural layer. Natural layer, we don't have much control. It will change with the environment. We are operating at the 30 degrees centigrade. There will be lubricant thickness on the surface. Now, we start operating at 70 degrees centigrade. There is a possibility that the layer get thicker, or there is a possibility that the oxidation rate increases. But there is a possibility also that they will start softening, and then because of the softening effect, there will be more and more cold welding, the hardness will reduce. So, coefficient of friction will continuously change and the temperature is going to change. Similarly, in environment, if there is a more and more moisture, coefficient of friction will change because of the thickness of the layer. To avoid that kind of uncertainties, we can think about solid lubricants. We can coat these surfaces with solid lubricants. One of the very popular solid lubricant used for the for the gears is a phosphating. So that we use the phosphate layers on a solid as a solid surface, solid lubricant on the gear surface. Now, there is a relation. This shows if thickness, if the shear strength of coating is a lower, then coefficient of friction will be lesser. Naturally, when we are talking about the shear strength of layer, it is a relative term. It is related to the parent material. Tau y is a parent material. I would say if there are gear and pinion, if they are made of the same material, then we are talking, we can take any tau y. But if the gear pinion is a softer material compared to the gear, or the hardness is a lesser or shear strength is lesser, then tau y will be the pinion material layer. So, the shear strength of pinion material. Now, this tau I is interface layer, whatever is the interface layer made. If we are using solid lubricant, naturally the shear strength of the solid lubricant will come. If this ratio is large, we say maybe tau y is 99 times of tau I. In that case, it will be very huge number and coefficient of friction will decrease drastically. But if we say now tau y is just 20% higher than tau I, naturally this factor will be 1.44 minus 1. So, square root of this, and that will factor is still will be very high, the coefficient of friction will be high. So, it depends what is this ratio. If tau I is much more lower than tau y, coefficient of friction will be much lesser, and we need to think solid lubricant from that point of view. And this is a diagram which shows that how if you keep gear surface in environment, there is a possibility of some contaminated layer on top of surface. Okay, the contaminant layer is oxide layer, some sort of a work hardening layer, and they are in angstrom. And what we discuss is that instead of relying on this layers which will change their thickness as per the environment, we better design lubricant layer as per our requirement. We think about the phosphate layer, we can think about the graphite layer, we can think about the molybdenum disulfide layer, and whatever is required we can design accordingly. Most often the solid lubricants are used in a liquid lubricants. We know very well if there is a solid lubricant deposited on the surface, what will happen? Under rubbing condition, that thickness layer will slowly reduce. It will not remain same. Or in other words, we are going to avoid the wear of gear material but we cannot avoid the wear of solid material, a solid lubricant material. If you are using Teflon, naturally Teflon powder form will come out, obviously it will be worn out from the coating surface. Similarly, if you are using the molybdenum disulfide and there is a rubbing condition, naturally molybdenum disulfide will be simply slowly removed from the surface. Same thing with the graphite surface also. So, in gears particularly, we cannot avoid the wear. We can only divert the wear from the gear surface or gear material to the solid lubricant material. We are not avoiding, we are not making it zero, wear will be there, but just we are changing the wear from gear material so that it can be diverted to the solid lubricant material. Now, if there is a liquid lubricant, what would the liquid lubricant do? It can carry those powder form along with it, and it can be again replenished or can be used again and again. So, there will be always some constant thickness layer, depends on the equilibrium, physical equilibrium, chemical equilibrium, there will be layer, and that is advantageous. Often we say 1 to 2 micron thin solid lubricant layer is sufficient. We do not require more than that. That is more than sufficient, but we know very well there will be some sort of wear out of this lubricant layer, and we do not want any time the lubricant layer turn out to be 0. So, we generally keep few micron, it can be 10 micron, 15 micron, depends on the life of the component and depends whether we are going to use liquid lubricant along with those solid lubricant or not. If you are not using any liquid lubricant, naturally we need to keep slightly thicker layer, so that component can be refurnished after a certain number of hours or certain number of operating hours. So, this is what a mixed lubricant, it was more like a dry lubrication with a solid lubricant. If I say a more appropriate word, solid lubricant also can be treated as a boundary lubricants. They are making a boundary layer. But what we are talking, when we use a liquid lubricant along with a solid lubricant, then situation will turn out to be mixed lubrication. What is the reason for that? Here the load carrying capacity will be shared by liquid lubricant, solid lubricant, metal to metal contact and full film lubricants. So, all four domain of the lubrication, all four mechanism of lubricant will be there. We can say this is a mu coefficient of friction. We are using the same relation which we shown in previous slide, but this tau I can be calculated as a weighted summation of different shear strength. The shear strength of metal interface, shear strength of bonded lubricant interface, shear strength of elasto-hydrodynamic lubrication mechanism, shear strength of fluid film lubrication. So, all lubrication mechanisms are present when we talk about the mixed lubrication. That is a name. We say that there will be solid lubrication and there will be liquid lubrication. So, naturally it will going to be a mixture of that, and we talk about the solid lubricant, we know that there will be metal to metal interface, there is a possibility of boundary layer interface. When we talk about fluid film lubrication, we can talk about the elasto-hydrodynamic lubrication, we talk about the full film lubrication where the complete surfaces are separated by liquid lubricant and sufficient thick lubricant layer is there, when there is a no deformation, there is no elastic deformation of the surfaces. So, there is a possibility. Now, when we talk about the metal surface and we talk about the designing those metallic surfaces, particularly for the gears, naturally we will not tolerate this metal interface. We do not want any time gear material comes in a contact with other gear material. So, this shear strength can be avoided. And of course, here we use the W1, W2, W3, W4. Summation of this W1 plus W2 plus W3 plus W4 will be equal to 1. We say that this we are using in the normalization form. We say that this is the weighted, these are the weights should be given along with individual shear strength. Now, we were discussing about we cannot tolerate metal contact. So, we try to avoid as far as possible in all situations. So, this parameter may not come when we are talking about the friction force for gear pair. This will not come. Similarly, this will not also come. We cannot tolerate a full film lubrication. we cannot transfer the motion 100% without any we say that loss of the velocity using the FFL. That is why this will not work, this is not going to work. Only two terms we are going to work with bond lubrication, and we are going to work with elastro-hydrodynamic lubrications, or in other words pressure or contact load will be immense in this situation. That is going to cause a deformation of surface, deformation of tooth surface, and we will be using some sort of boundary additives. It will not be the only liquid lubricant, but we need to use a boundary lubricants so that wear of the surface is minimum. When there is a extensive elastro-hydrodynamic lubrication, it is even we say that there is a mechanism like that, still the surfaces are going to come in a contact. And to avoid that metal to metal surface, we need to use boundary additives, and this is the what we say. Now, if I say that tau mi is not going to work, tau FFL is not going to work, naturally this will be 0, this will be 0, and we have only two mechanism, that is a boundary lubrication mechanism and elastro-hydrodynamic lubrication mechanism. Now, these two mechanisms, and there is a weights. Naturally, these weights will be different now. Initially, maybe we say this was a weight was some value 0.1, 0.2, 0.3, and this value are something like 0.1, 0.2, 0.3. But we are talking about the gear lubrication mechanism, naturally this W1 is 0, W4 is 0. That is why we are not taking, we are not accounting tau mi and tau FFL. Naturally, these two values will differ. Now, there is a W prime 2, W prime 3, and this summation will be equal to 1, or in other words, say W prime 2 plus W prime 3 will be equal to 1.0. In other words, if I say alpha is used as a weight factor, naturally other factor will be 1 minus alpha. So, this is a proper shear in strength formula which can be directly substitute here, and we can figure out what will be the relative coefficient of friction. We are not talking about the absolute coefficient of friction. Whenever we compare, this is going to be a good comparator. But if we talk about the absolute coefficient of friction, it depends on many parameters, many factors, and we cannot really estimate mathematically what will be exactly coefficient of friction at the interface. We need to do extensive experiments for that. But if we want to compare different material pair, if you want to compare different hardnesses, if you want to compare different lubricant, if you want to compare different profiles, yes, this kind of relation can be used. So, this is a relative parameter. Obviously, it can be used as a comparator, but cannot be treated as an absolute value. And this is what we are showing a figure where the image of a liquid lubricant have been shown. Obviously, that photograph of a liquid lubricant is shown. What we did experiments on a gear pair in our lab, and what we found when we were using initially this kind of the fresh oil, yellow oil, and good oil, as like it shows that it is a liquid oil. After maybe doing 100 hours operation, when we removed the oil from gearbox, we found this kind of a color. This is a completely black, and we could not find separate particles, but this liquid is filled with all of wear particles. Now, there is still surface damage happening, and we can say that is a clear indication that whenever we operate a gear pair, they are going to work with a mixed lubrication mechanism. They are not going to work with a full film lubrication, they are not only going to work with the EHL. So, these two lubrication mechanisms, maybe last one can be rejected, this can be considered, but there will be boundary lubrication, and if there is no sufficient boundary additives available, then metal interface will come. But we know we are more careful about the gear pair. We know in manufacturing costs on the higher side, and they are very sophisticated components, they are very important components. Naturally, we will be using some sort of boundary additives, and whatever the boundary layer is made, maybe it is made with the chemicals, or the chemical layer is made as a bonded lubricant layer, it is not only the solid lubricant, then this kind of a lubricant and this kind of color of the liquid lubricant will emerge. That is obvious. Okay. Even chemistry is happening, obviously that chemical action is happening, or when we are talking about some sort of chemical layer on the gear pair, naturally some metal is going to act along with oxide or getting oxidized, and when it is removed, naturally it is going to make a color like this. So, that is important to consider. What I was talking about what we have done in the lab. So, this is a setup which is just demonstrating the what we did. So, this is the 10 HP motor, there is a belt drive, and this is a gearbox. Naturally, gearbox need to be loaded that is why it is connected with spiral coupling, and this is a torque sensor, and there is a dynamometer. This dynamometer was made in house. We could apply up to 20 Newton meter torque, but completely controlled condition. When we operated for the 100 hours, what we got? When you open the gearbox, what we are getting is completely filled with a black color oil, and even this particle you can see that the kind of the color of the oil here, if we use a fresh oil, it will not be this kind of thing. It is generally a yellow color oil, but here it is turning out to be slightly blackish, and these are the gear teeth. It is also having some sort of the black oil on the surfaces of gear teeth, and this is what we showed, that it is the accumulation of some wear particle in the soil or completely submerged of these particles. So, when we do experiments, we 100% know that it is not going to be a full film lubrication mechanisms, and we are using liquid lubricant. Naturally, it is, if there is a wear will happen because either directly removal of material or some oxidants of that metal. Now, that clearly indicates when you talk about gear pair, there will be wear of a surface, but this wear can be reduced when we talk about the power loss or when we talk about the friction loss. We can say that two surfaces, they come in a contact, they need to have a lesser friction resistance, but there is a problem. We require intimate contact between two surfaces so that the relative velocity is 0. I would say tangential relative velocity is 0, and that is what we say the efficiency. We want complete velocity to be transferred from one surface to other surface, and that is basically with the friction mechanism. Because we have used the involute profile or the positive drive profile for that, but still there is a problem. We want minimum friction and we want good friction also. So, we come up with some sort of trade off. When you talk about the friction force, and we know very well that friction force is going to work between the gear teeth, but we cannot term it as it is, reason being that there is a velocity which is doesn't remain constant. Obviously, the sliding velocities doesn't remain constant. It's going to be constant or the 0. Sliding velocity will be 0 at only the pitch point. Away from the pitch point, velocity is going to change. And if, of course, in some gear pair, even there will be sliding at a pitch point, which we have studied in previous lecture, and I am just repeating this slide with a few observations from the previous lecture, where we say that with involute profile of the gears, only one contact position experiences pure load. Pure loading happening only at the one point. Now, as contact moves towards or away from the pitch point, sliding is going to occur. There is a bound of this, that sliding will continuously increase if we move away from the pitch point. Then another example was given. You say in the case of crossed axis rolling gears, where the axes are not parallel, they are not intersecting, they are not coplanar, and they are out of the plane. Naturally, there will be some component in the third plane or third direction also, which is going to create additional sliding. That is why you see in the case of the cross axis rolling gears, velocity component in axial direction will occur, and that is going to increase the sliding. overall sliding will increase in those situations. That is why when we try to compare different gear pair, obviously that different gears, what we get. Say type of the gears, efficiency. This is table shows that how efficiency or the what kind of efficiency we can achieve. Simplest one to manufacture, easiest to analyze is spur gear. We say the shaft axes are parallel and length of was a bearing gear width is also parallel to the axis. Efficiency is pretty high, it's 97 to 98%. Of course, we are talking about a good condition. We are not talking that we are using, we are not going to use any oil or something like that. We are talking about the good conditions, all good conditions. The spur gear shows a 97 to 98% efficiency in good conditions. Coming to the bevel side, in previous lecture we mentioned there is a spur gear works on cylinder as a cylinder, while bevel gear work as a cone on cone. They roll on each other. So, bevel gear when axes are intersecting, maybe 90 degrees, 60 degrees, 70 degrees, depends on kind of the geometry. They show again in ideal condition, good operating condition, efficiency as a 97%. However, if we offset it, gear axis, there is some gap. The efficiency is slightly lower, the 94 to 96%. We say that offset is very minute, then efficiency will be high. Offset is a greater side, then efficiency will be 94%. Now, these are the all parallel axis related options. When talk about the cross helical, where the coplanar or the surfaces are not there or the axes are not in one plane, then efficiency you can see is reducing drastically. Helical gears otherwise are good known gears, or they work with a lesser noise, much better performance. But when we are talking about the crossing of that, obviously that instead of line contact they have a point contact, then efficiency is dropping from maybe say 100% to 84%. That is a substantial change. Well, when we work with a worm gear, the torque ratio is almost 40 to 1. It's very high torque ratio, but sliding also will be very high in those situations. So, efficiency goes down in these situations. When sliding is very high, naturally efficiency is just 30%. When we are able to control it properly related to low sliding velocity, the efficiency can reach to 97%. But of course, these are the very exceptional cases. Generally, efficiency of worm gear is lesser than 90%. So, this gives an idea that these are having a lesser efficiencies, so which is the efficiency having lesser than 100%, naturally there will be some sort of power loss. And we can talk about the friction loss and multiply with the tangential velocity, but that is not in our case. It will be a very simple case. Here the sliding velocity is going to change continuously as we move away from the pitch point, and it always happen in one contact. We say one tooth pair contact, only one point will be at the pitch point, all other points, maybe say there are 200 points, 300 points, or whatever the way we divide it, there will be different sliding speed, and the continuous point there is change in the sliding velocity. Naturally, we can have to talk in terms of power loss, we cannot talk just in terms of friction losses. So, we say the one of the major factor in power loss. When we talk about the gearbox, actually there will be shaft, there will be bearings and all, but when we just talk about the gear pair, only the contact is happening at the tooth. Naturally, there will be a toothing power loss. Otherwise, if we talk about these surfaces, these tooth surfaces, they are not under load. So, power loss due to the load will happen over here only, while power loss without load will happen on number of other teeths. As there will be some sort of dragging action, this is a solid metal, and if it is dipped in the liquid lubricant, naturally there is a splashing will occur. I will try to splash lubricant out. You can see there is a discontinuity surface. If there is smooth surface, then there will not be problem, but this surface, because of the meshing requirement, they are discontinuity. Naturally, there will be more and more splashing loss, more if I can say ideal power loss. We are not talking about the load transmitted through these systems, we can be talking about the churning effect. It is going to churn the liquid lubricant or going to cause a loss of the load. If viscosity of the liquid lubricant is higher side, naturally this will churning loss will also be on the higher side. So, we have a two power loss. When we talk about the two thing power loss, the ideal power loss when the load is not there, and there will be load power loss. And naturally, when we talk about the excessive load, we talk about the elastohydromal lubrication, we talk about the mixed lubrication, actually this component is going to play a major role. And this can be given as FR, friction force into velocity, into sliding velocity. To be on precise side, we say friction force should be presented in terms of a normal load, and that is a mu. Normal load is a mu Wn, but the coefficient of friction is a mu over here. So, it is a mu Wn into Vg. This is going to change. Question comes, will mu be changing really, or is going to be constant? Will Wn change or will remain constant? So, these two are important aspects, or in fact, if you take my words, mu cannot be constant. We know the loading points are going to change, applied load is going to be changed. It may vary from 0 to the kilonewton load. As a load is such high variation at the point of contact, naturally mu is going to vary continuously. Talking about Wn, again the point of contact is continuously changing, or line of contact is continuously changing. Naturally, this Wn will not remain fixed, is also going to change. So, mu is going to change, Wn is going to change, and Vg is also going to change. Naturally, we are talking about the power loss, which is average power loss and mean power loss. And that is why you say that these parameters are not constant, they are going to vary continuously in magnitude and maybe direction also. And interesting thing is that mu itself is a function of number of parameters. Okay, that is why it is a mu m. This is the mean value, average value of coefficient of friction. It is a function of itself, load. It is going to depend on the load itself. It is going to depend on the bearing or the gear length. If the length is increasing, naturally this loss will be high, or mu will be higher side. It is going to depend on the pitch velocities or summation of pitch velocities. It is going to depend on the liquid lubricant viscosity, carrier fluid viscosity, and it is going to be a function of surface roughness. A larger the surface roughness, larger the value of mu. So, this is difficult to find out through the science. It has been shown, if I take a constant value, if I change any of this parameter, mu is going to change. Of course, the sensitivity of the parameters is different. Talking about this R, the surface roughness, it is a composite surface roughness. Naturally, the gear flank surface roughness will be accounted. If the gear flank of the pinion as well as the gear flank of the gear. Obviously, both the surfaces will surface roughness of both the surfaces will be counted, and generally it is a RMS value which is be counted. So, we know mu m or the mu, even the mean value is going to be a function of so many parameters, and many times it is difficult to prove through the science, but when do number of experiments we can find out using curve fit equation. We substitute, we use these parameters, 3-4 level parameters, do experiments and find out what will the mu. So, it is going to be decided based on experiments or curve fit equation with some unknown constant which need to be determined through experiments. Now, what we are talking about we use the word the normal load Wn. Question comes, what is this Wn? You say this is a gear pair. Now, any surface perpendicular to that should give me normal load, something like this. This is a Wn. Question comes, how to find out from where this figure will turn out? What is mechanism? Yeah, we have some sort of pressure angle, and we know pressure angle, if I account the pressure angle, I will be getting two components. We say Wt tangential components, which is going to drive the gear pair, and Wr, that is a radial load, is going to push gear away from other gear, is going to be penalizing the bearing. So, there will be radial load on the bearing. So, how to find out this Wt and Wr? That is another question. One way is that we generally know what power to be transmitted. When we know power to be transmitted, and that too in a rotational direction. So, we can figure out this. However, before that we need to find out the relation between Wn, Wt and Wr, and they say the Wt will be Wn into cos phi. Naturally, Wn is going to be greater than Wt and Wr. We can say, if we can take a square root of this as a vector summation of Wt and Wr, we can find out Wn. So, this Wn will be maximum load, and Wr which is there need to be minimized, so that bearing is less loaded or subjected to less load. Now, we talk how to figure out Wt, or we say that any of this W, once I know that any of W, and if I know the phi value. Of course, this phi again will change. The pitch circle diameter generally is known, but away from the pitch circle diameter is generally not known. We need to find out from the geometry. Now, this Wt can be given in terms of torque by pitch circle, which is the radius. Pitch circle radius for the pinion will be Rp. Similarly, for gear it will be Rg, and generally Rg is a lesser, Rg is a more than Rp. That is why we are using this relation. We want on more on conservative side, and that is why we are taking higher value of Wt. So, Wt is a torque will remain same in both the cases, or not remain the same, it will be power will remain same, the tau into omega will remain same. So, the torque, whatever the torque on the pinion divided by Rp, that is going to give us a relation. Now, once we know this, we can figure out what will be the Wn, and that is turning out to be Wn is a torque divided by Rp and divided by cos phi. So, once we know Wn, we should be able to find out the frictional losses. The question comes, we are trying to find out this Wn through using this relation, but am I doing the right job? Is there any possibility that only one pair in a contact, and we know there will be some sort of clearance. If this gear tooth go in this spacing, to avoid the jamming, we keep some extra clearance. Naturally, that means when the one tooth pair engagement is over, there will be some clearance, and that is going to give a jerk. Naturally, we need to design gear pair in such a manner, before losing first contact completely, other pairs should start contacting it. Then only the smooth transition of the movement will occur, through a smooth transition of the power will occur. From one shaft to other surface shaft, power can be transmitted when there are more than one pair of the teeth in a contact. Maybe at the pitch point there may be only one pair in a contact, but away from the pitch point, maybe just the start or the just end of that, naturally there need to be more than one or two pair minimum to be in a contact, so that we get a transmission. When it happens, naturally this Wn calculation is not going to be right, because there will be some sort of load sharing, and if there is a load sharing, we should account that load sharing effect. And what we say, we should use a contact ratio, and contact ratio is generally more than 1 to be designed, and more than 1 means there is a load sharing at the extreme points. At the pitch point, yes, there may be the same load, but at the extreme points there will be different load, and we need to evaluate the power loss. We need to find out the load at the different points, because the sliding velocity is also going to change. So, if you want to find out the power loss of the different points, we require force, normal load at those points, as well as we require a sliding speed, and that is why we require all these calculations. Now, here it is written contact ratio, so many question marks. How to find out this contact ratio, that may be the bigger expression we will try to figure out, and but this value mostly for spur gears it ranges from 1.4 to 1.7. So, maybe assume that lowest value should be 1.4, whenever we design it should be more than 1.4. When we talk about the helical gears, the contact ratio is generally on the higher side, that is 2.0. That is a reason why helical gears work smoothly compared to spur gear. The engagement is gradual, and most of the time two pairs are sharing the load, and that is advantage. Because of this advantage, many times people go ahead with the spur gear geometry because of the less complexity, but they try to make a high contact ratio gears. They change profile to some manner. We say that they add addendum and the dedendum, larger addendum and dedendum, so that gear is modified to give us high contact ratio. Contact ratio is greater than 2.0 in those situations, and generally that gives us a smooth operations that give us the lesser load on per gear teeth or gear tooth on the particularly for pinion and gear. Now, a question comes how to figure out how to estimate this contact ratio. So, that can be done mathematically. First, we can give some sort of description. Say, assume this is one sketch, and this is the one point, this is another point. We say the beginning of point and the end of the point, and this arc can be known as angle of approach. When the gear teeth start contacting, reaching to the pitch point, and after that angle of recess, try to depart from that pair, right. So, there is angle of approach, angle of recess. If we know this angle, or we can estimate what is the arc length. Arc length on the when they are coming under contact, and if we are able to estimate, we will based on that we can figure out what will be the contact ratio. In other words, we say contact ratio can be given as a length of action, the whole length of action, and when they are coming in a mechanical contact, we assume that whatever the curve which we have shown over here, if we know the length, that means that this is in the polar coordinates, we can transfer to the rectilinear coordinates. We say effectively we can say that this curve, if it is developed in a straight line, that will give me length of action, and divide by the base pitch. Okay. Now, the base from where it is started, from where the gear teeth is started, that those if that pitch is known to us, we will be able to find out the contact ratio, or we can say contact ratio is defined as a ratio of the length of action divided by base pitch. And this length of action can be divided in two parts, so length of approach and the length of recess. And base pitch can be figured out by finding the periphery of base circle divided by number of teeth. So, Zg here is the number of teeth, Rbg is a base radius of the gear. So, we are talking of the gear pair over here, maybe we can think about the pinion also, but here it has been used the word gear as G. So, base pitch radius of base circle is Rbg, number of teeth on the gear is a Zg, and we are talking about the circumference, which is the 2 pi r Bg is giving you circumference of the base circle divided by number of gear teeth. That is going to give as a base pitch, and that once we know the base pitch, we know the length of approach, length of recess, we can figure out what will be the contact ratio, which is important to evaluate what will be the normal load on per teeth or per tooth, right. So, to be on a surplus side, we can draw this line sketch. Say, assume this OP as the center of pinion, OG as the center of gear. Now, point C is a pitch point contact. So, there is a straight line in this case. We know length of action will be at some angle with this, and this is a starting point, or so the A star is a point where the contact should start, and B star is a point where the contact should end. But we know there will be a lot of discontinuity. So, what we do, we provide some sort of flit at the start of contact and end of the contact. So, the excessive stresses are avoided. That is why in reality contact starts at the A and ends at the B. It is not A star, it is not a B star. So, actual contact starts after the base cycle, it is not at the base cycle point. We use some sort of fletting there. So, this is A, and end also, because a tooth we generally do not give very sharp edge, we give some sort of the flit there. So, the tooth also will be departing, or the separation will occur before the B star, and that is assuming that B. So, this is A to B is a length of action, and we need to find out this length it's exactly. We already know that what will be 2 pi r bg divided by z g. This is generally geometry parameter known to us before operation, but this action is can be calculated based on the operating parameters. So, we say we need to figure out what is the length of approach, what is the length of recess, and once we know that, we will be able to find out what will be the contact ratio. Right now, to find out the contact ratio, we can start finding some parameters, some lengths. We say A star C. The length A star C can be figured out, can be given in terms of RP. We know this is a right angle triangle, okay, and RP is generally parameter known to us at the start, particularly from the manufacturing point of view. So, RP is if it is known, and this is the sine phi, this is the phi, we know that this is a attitude angle. So, we take that, and that is why the AC can be given, or say the A star C can be given in terms of RP and sine phi, that is given over here. Now, we can figure out this length also, A star B. Again, there is a right angle triangle. A star B can be figured out using this relation. We can directly, we can take this ROP also in terms of that, and we can find out this using those relations. So, this is a ROP given, this is the length of OPB, that is ROP is outside diameter of the gear, if that is known, and this is a base radius is known to us. By subtracting this, we can figure out what will be the A star B. So, that is why it says the length A star B is a square root of ROP square minus RBP square. Now, what is interested to of our interest is AC length and CB length. We know in first case we figure out what is A star C, and second case we figure out what is A star B. Now, if we subtract this length from the complete length, naturally CB will be known to us, and that is given over here. The length CB is equal to A star B, complete A star B minus A star C. We can substitute these values. This is, or in mathematical terms, CB can be given as a square root of ROP square minus RB square minus RP. This is the pitch circle radius into sine phi. Sine phi, the sine phi is known to us from a geometry point of view, from a manufacturing point of view. RP will be known to us from manufacturing point of view. This also will be known, so that we will be able to figure out what will be CB. Now, we do the reverse order, we can figure out what will be the AC, or we can start from here, we can find out what will be the AC. And that is why we say that similarly AC can be figured out from in terms of ROG. Here what we figure out in terms of opinion, here we are trying to figure out this value in terms of gear. So, ROG square minus RBG square, so both are the opinion, the outer diameter of pinion, outer diameter of gear, this is the base diameter of gear. I would say radius, in terms of radius, this is the radius of outer radius of gear and the base radius of gear, minus again pitch circle diameter we are using. So, pitch radius into sine phi, assuming that there is the same pressure angle for both surfaces. Using this, what we say, overall length will be CB plus AC, and that is what we say AB. The C is common, and this will be turn out to be the first parameter related to pinion, second parameter related to gear, and this will be summation. Now, we can use through the find out the contact ratio. So, contact ratio can be given relation, there is a numerator, this is a denominator. Once we know what is this center distance, C is the center distance, the summation of RP plus RG. Right. Once we know these values, we can figure out what will be the contact ratio. Based on the contact ratio, the contact ratio is 1, naturally we know that the friction losses will be tremendous, but contact ratio is lesser, the friction losses will come down because Wn will come down or will be reduced. And it has been shown that contact ratio over the period of time will continuously decrease. Initially, when the gears are new, contact ratio will be larger. As it progresses or as the wear out starts, then this contact ratio is going to decrease continuously. That is why we say that if I spur gear, if I want 1.4 as optimum value, I should be able to keep it slightly on a higher side. Otherwise, there will be some problem later, maybe say after 10,000 hours or 15,000 hours of operation, the gear will wear out and will start giving much lesser contact ratio. That lesser contact ratio is going to reduce the stiffness of the system and the vibration will start. Obviously, that there will be some sort of jack motion, there will be some sort of impact motion and the noise will start. To illustrate this, I have one example. I will just try to elaborate that. And what this indication over here, contact ratio should be more than 1 always whenever we design. Now, just for the elaboration, I am just giving one example how to use this parameter. Here the manufacturing data are given that phi is equal to 20 degree, number of teeth on a pinion is 19, number of teeth on a gear are 37, module is 4. So, what we find gear ratio, the simple Zg divided by Zp, circular pitch to be figured out, base pitch diameter, center distance, what will be addendum, these are standard terms, addendum, hole depth, outside diameter and contact ratio. In addition, this is given if the center distance is increased by 2%, what will be the new pressure angle, new contact ratio. So, we will say the contact ratio is given by this relation which was shown in previous slide, and gear ratio is simple, number of gear, number of teeth on gear divided by number of teeth on pinion. Circular pitch is the 2 pi r g divided by number of teeth, and when we want to find out the base pitch, that it will be multiple of the cos phi. That is why this P b can be directly substituted over here. Whenever we have a module and a number of teeth, we can find out what will be the pitch diameter. It is just simple multiplication. Module into number of teeth is going to give us the pitch diameter, and that is what is being given. The pitch diameter of the gear is mzg. Similarly, pitch diameter of pinion will be m into zp. And once we know the pitch diameter, we can figure out what will be the radius, pitch radius. Summation of pitch radius will be equal to center distance, and we are using the word nominal pitch center distance, the nominal center distance, reason being that these values are hypothetical, may change during assembly. Addendum and dedendum, they are generally manufactured with cutters, and we say that standard thing is that there will be 1 m dimension above the pitch circle, the pitch radius, and below distance between the base circle and pitch circle at any time, thickness between these two will be 1.25 times of module. So, A is given, B is given to us, we can figure out all the parameters and we can figure out what will be the contact ratio. Now, if we find the contact ratio, it will turn out to be say 1.62. And second part in this case is given that if center distance is increased by 2%, if the center distance is increased by 2%, that means C is increased by 2% and that is being given, the base pitch also will be will remain same, but RP will change and that will increase 2%, and that is going to give us a new angle, new pressure angle. So, this new pressure angle will be slightly greater than 20 degree. What we will do, in the next lecture we will continue with this example. I will just repeat this slide and elaborate it, and we will show some sort of calculation with this kind of example, and we will continue with the friction and lubrication of the gears. Thank you. Thanks for your attention.